Hello, everyone. Welcome back. Today, we want to learn about the law of sines, how we can use the law of sines, understand what it is, how it can use it to help us solve non-right triangles, triangles without a right angle. So, our goal is then to understand the situations which we use to solve a non-right triangle. We can't necessarily solve every one, depending on what we're given. Understand the possible outcomes, and then be able to use the law of sines to solve non-right triangles when we can. But first, let's explain what the law of sines is and talk about what we mean by, of course, a non-right triangle. So, of course, we know a right triangle is a triangle with a right angle. So, a non-right triangle is just a triangle that doesn't have a right angle. And generally, you can have sort of two situations. So, you could have one situation where all your angles, let me draw that better, where all of your angles, all your are less than 90 degrees. Okay, I know it's not a very good triangle, but it's okay. So, this is our uh, we call this angle A, angle B, and angle C. And then we have opposite sides, side A, side B, and side C. And this is an acute triangle because all the angles are less than 90. But we could also have a situation where we have a triangle like this, okay? Where once again, this is our angle A, B, and C. And side A is here, the opposite side of angle A. Opposite side of side B is this, and opposite side of side C is small c. And this is an obtuse triangle because we have an angle that's bigger than 90 degrees. Okay. And so potentially we can use the law of sines for either one of those cases, but that's what we're talking about. So a triangle that without a right triangle basically have these two categories. Now, so we have a situation like this, then we use what's called the law of sines, which looks like this. So I'll just rewrite this here. It says in a triangle like these, that's what the law of sines says. As you can see over here, that the sine of A over side A is equal to the sine of angle B over side B, which is equal to the sine of angle C over side C. Okay. Now, what that means is that these are all equal. So you could have this part equal, the part with A equals C or the part with B equals C, any of those combinations. Okay. They're all equal. And also, you can do this, your angle can be either in radians or degrees. Most time work with degrees since a lot of times we can applications. Okay, but we can work with radians. Now we can also say, or we can also remember you can take the reciprocal of both sides of any equation at the same time. It's still equivalent. So we can also write this as side A over the sine of A equals side B over the sine of angle B equals to side C over the sine of angle C. That's also an equivalent way to write it. And sometimes it may be more useful to use that version. Okay, so let's talk about when we can use the law of sines. So basically, for example, if we use this, okay, we try to use this part to solve, then obviously we have to know we have four different things here: angle A, angle B, side A, and side B. So we have to know at least three of those to find the fourth. So that kind of guides us in determining what types of situations we can use. Let's say, so the law of sines is used when we know two angles and a side. Okay, and that's because, remember, as long as we know two angles, we always find the third, because for any triangle, all the angles have to add up to 180. So, um, so we use the law of sines. We use or what we call angle, angle, side, or um, angle, side, angle. What we mean then specifically is, once again, here just use some basic just acute triangles. Okay, so let's say we know this angle and this angle, maybe this side here. Okay. Oh, I'm sorry, I put the angles in the wrong place. So maybe I know that rather this angle and this angle, 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 and make that side. Okay. Or if we know two angles and the side between them, okay, so this angle, and this side, that will also work because we can always find the third angle. Okay. Now, We can also use it for what's called side angle, although there's some circumstances I have to be careful about. Okay. What we mean by side angle is if we know two sides, let's say I know this side, and an opposite angle. Two sides and opposite angles. So I know, for example, these two sides have to know one of their opposite angles. It could be either this angle here or this angle here. Let's say it's this one. That will work. But it has to be an opposite angle of one of those sides. Okay. Now, as we'll see, there can be some different things happen here. You can actually get what's called the ambiguous case, because this can actually have no triangle. You can have two triangles, just one triangle. Okay. This is called the ambiguous case. And I state all this over here. Actually, let me just rewrite that. This is called the ambiguous case. So it's not always clear what we're going to get, but we'll talk about some examples of that. Okay. Now, we can't or cannot use for a couple cases. One is called side angle side, or if we know all three sides. Okay, so let's talk about that. So what we mean by side angle side is if I know, let's say this side, and the angle in between them. That's why it's called SAS, side angle side. Okay, and that's because, look back to the law of sines. Okay, for example, here, then basically the way it works, I have to know a side. If I know two sides, for example, I know side A and B, I have to know one of the opposite angles to make it work. Okay, that's why I can use it for side angles. I know at least one of the opposite angles. Okay, but if I don't know an opposite angle, and here, since I only know one angle, I can't find the other two. It's still true that all the angles have to add 180, but I don't know the other two. So you have to have at least an opposite angle to make the law of sines work. Okay, and of course the side case, all three sides, then of course you have to know at least one angle to make the law of sines work. In these cases, we're going to use the law called the law of cosines. We'll see that in a different video. Okay. Now, one more thing, a couple more things to mention. I basically say all this over here. If a triangle exists, it can always be solved. What I mean is, if you actually have a physical triangle, or if you're given an accurate picture of a triangle, you actually know what all the sides, at least how everything is laid out, then the solution will always be possible. But if I just give you some numbers and I say these are angles and sides, that may or may not always give you a triangle. It just depends what you're given. So that's why you have to be careful. Okay, let's look at some examples. Our first example. And so what you're going to say, our direction is to solve the triangle. Okay, number one. So let's say I have a triangle looks like this. I'm going to draw a picture. It's kind of some of the pictures I've been drawing. So I have kind of an acute triangle. All angles are less than 90. And let's say, actually, hang on just a second. I'm having trouble reading my own writing there for a minute. So I'm going to make sure I have my numbers right. Okay, yeah, here we go. Okay, so let's say this angle is 45 degrees. This angle is 105 degrees. I actually take it back. This is actually an acute triangle, or an obtuse triangle, because this angle is actually 105 degrees. Okay, I'm writing my angle symbol too large. I want to make sure it's clear that's 105 degrees, not 1,050 degrees. Okay, let's say we know this is our angle A. This is our angle B. And of course, angle C is not given. This is side A. Of course, this is side B. And side C is given, which is 10. Okay. So I want to use the law of sines to help us with this. Now, in this case, this is the one of the angle sine cases. Okay, actually, technically, this would be the angle side angle case. So it doesn't matter. As long as you have two angles, you can always, the law of sines will always work. Okay. In this case, we do have two angles. All right. So we need to find angle C and then sides A and B. What a better B almost looks like an L. So side B. So I need to find angle C, which we'll do easily, then find side A and B. Okay. Now, also one thing that's careful, we have to be careful to remember here is that this is not a right triangle. So we can't just use the regular trig functions. Also, we can't use the Pythagorean theorems. This is not a right triangle. Okay. Now, actually, the easiest thing is to find C, since we know two angles. Then C, of course, is going to be equal to just 180. This is true for any triangle. 180 minus the sum of the other two angles, 45 plus 105. We know it should be an acute angle. So side C, or angle C, rather. And I'll just do that on my calculator. And so that's just going to be 30 degrees. Okay, so I'll just circle that so we can keep track of it. So angle C is 30 degrees. Okay, now let's find either side. Now we know all the angles. It doesn't matter which side we use. Let's find side A first. So it doesn't matter. Okay, and so if we do that, then actually the best thing to do, if you use the law of sine, the best thing to do is use it in this version. Okay, the reciprocal version, because we're looking for actually side A. And so let's actually use, so we're given side C, so we're going to use this. So A over sine of angle A equals C over sine of angle C, since we're given what we called side C. Okay, and let's do that. Okay, so that's going to be A over the sine of angle A is equal to C over the sine of angle C. Okay, now let's just plug in everything. And so we have A over the sine of angle A, and angle A was 45 degrees. And this is going to be C, which is 10 times the sine of angle C, we just found to be 30 degrees. The sine of 30 degrees. Okay. Now I'm actually going to write this a little bit this way. So actually, if you multiply both sides by, remember, the sine of 45 is just a number. Sine of 30 is just a number. So multiply both sides by the sine of 45. So A is going to be sine of 45 degrees times 10 over the sine of 30 degrees. Actually, then I'm going to just go to Desmos and do that. So go to Desmos. Sorry, I have a all right. So, and one thing you need to make sure, since you're going to be in degrees, switch to degree mode in Desmos. So go over to the upper right corner, click on the wrench, click on degrees, and make sure in degree mode. Otherwise, I'll read those angles as radians, which will give you a wrong answer. Okay. We said it's going to be the sine of 45 degrees times 10 divided by the sine of 30 degrees. And what's going on? Let me put parentheses around this. Maybe it's trying to read that and is taking the sine of all that. Yeah, I guess it is. There we go. Okay. Yeah, so maybe you put the parentheses around that and makes Desmos or whatever your calculators realize you're not trying to take the sine of all of that. And so that gives us about, let's round to two places, 14.14, and also didn't have units, so just 14.14. Okay. So A is equal to 14.14, two places. Now, once again, we now know two sides, but we have to resist the urge to use the Pythagorean theorem because it doesn't work in these cases. So let's actually find our last thing, which is to find side B. Okay. And here, once again, we use the law of sines again. I shall use this version here. This is so inverted. So essentially these two equal to each other. So we're going to use B over the sine of angle B is equal to C over the sine of angle C. Now plug everything in. And so we have B over the sine of angle B, and the sine of angle B, whose angle B is 105 degrees, is equal to C, which is 10, over the sine of C, which is 30 degrees. Okay. And just like before, this is going to be like similar to the other one. This is going to be B is equal to the sine of 105 times this fraction, 10 over the sine of 30. And we'll just plug that into Desmos or plug it into your calculator. You can just do it just this way. That way your calculator will keep all your significant figures. So let's do that. So go back to Desmos. So let's use parentheses this time. So the sine of 105 degrees times, then actually I'll just copy and paste this. Okay. And that's going to give us then two places again, 19.32. Okay. So 19.32. Side B is equal to 19.32. We didn't give units on this, but if you want to put in units, like meters, feet, whatever. Okay. So let's take a look at our triangles. What has to be true about any triangle, right triangles or any triangles, is that basically the larger your opposite angle, the larger your angle, the larger its opposite side. So if we compare this, then B was the biggest angle, should have the biggest opposite side, and it was 19. A was the second biggest angle, or sorry, yeah, A was the second biggest angle at 45 degrees. So you should have the second largest side, which it did, was 14.14. And then C is the smallest angle, 30 degrees, and has the smallest opposite side, which is 10. That doesn't always guarantee you're right, but at least you know that your angles and sides are in the right proportion to each other. Okay, so that was an example then of using the law of sines. Let's look at number 2. All right, now this time what we're going to do is actually give you a this time instead of drawing the triangle, I actually give you some of the values. So let's say our side A is 3, side B is 2, and angle A is 40 degrees. Okay. Now we're going to draw a picture. We have to be careful though, because you're not sure exactly if this is going to look like this. So I'm drawing this as this triangle, but it might look exactly like this. But at least we can, have something to see and kind of put everything in proportion. Okay. So side A, this is angle A, which is 40 degrees. Side A is 3. Okay. Side B is 2. And then, so here what we need to find then, obviously we need to find, and this, if you notice, this is the side angle case, because we're given two sides and one of the opposite angles. So this is the one that can have some, it's called the ambiguous case, because you can have, you said you can have one solution, you can have two solutions, you can have no solution. Let's take a look at this one though. This should actually give us only one solution, and we'll see why. Okay, so what we need to find then, we need to find our sides. We need to find side C, and also need to find angles B and C. Now, what we can find first kind of depends on our law of sines. So let's take a look. So for angle B, for example, do we have enough to find B? Okay. Yeah, actually we do. So if we take a look at this, all right, we know side B, we know A, angle A, and its side opposite side A. So then we can find B this way. Okay. Let's do that first. Although it's necessarily the first thing we have to do. Okay, so let's use that relationship. So let's do the sine of angle B. I'm having trouble writing letter B sometimes. The side of angle B over side B is equal to the sine of angle A over the sine of A. I apologize, it's we're writing today. Okay, so let's going to plug in everything. And if we do plug in everything, what we get is, so we have the sine of angle B over B, side B, which was 2, is equal to the sine of angle A. So angle A was 40 degrees. And that was over side B, which is 3. Okay. Now, as we can see, just multiply both sides by 2. That's going to give us the sine of angle B is going to be equal to 2 times the sine of 40 degrees over 3. Okay. Now, let's approximate this. Let's use Desmos, and we'll get a approximation of several figures. So 2 times then the sine of 40 degrees, I believe. Yeah, 40 degrees divided by 3. Okay. Now, since we're going to take a sine, let's actually do several figures. In fact, let's go to 5. So 0.4285. So if we go to the fifth place, it'll be a 3. So 42853. So 0.42853. Okay. Now, let's do the inverse sine of that. So if you take the sine of both sides, you'd have B is equal to the inverse sine of 0.42853. Okay. Let's find out what that value is. Now here, once we get the value, you have to think about it a bit more. So B okay, let's do that, the inverse sine on Desmos. So to get inverse, your inverse trig functions, click the keypad, then click functions, and you see the inverse trig functions, inverse sine of 0.42853. Let's get we're in degree mode. So about, let's do 27, let's do 2 places again, at 25.37 degrees. Now, here's what we have to think about, in addition to the usual things. Now, let's draw a set of axes, which are 0 degrees, 90 degrees, 180 degrees. Now, since we're talking about an angle, then here, this, of course, one possibility is 25.37 degrees right here. But since we're talking about sine being positive, okay, so sine of theta is positive, is greater than 0 in quadrants 1 and also in quadrant 2. So it's possible we can also have an angle over here, okay, where this, or actually I have to move this out of the way. Here's 180 degrees, where this angle here is also 25.37 degrees. Okay, so also need to find this angle here. Just do that, just subtract 180 minus 25.37. I'll do that on my calculator. So 180 minus 25.37. And so another possibility is 154.63 degrees. Now, both of these will give us a sine, okay? Both of these will give us sine beta is equal to that, okay? If you want to check that, we can do that. So let's go to Desmos really quickly. So let me just write these down, 25.37 and 154.63 approximately. Let's go back to Desmos and I'll show you what I mean. Okay, so now if I just do, get rid of the keyboard. So sine of 25.37, right? So that's, it's not going to be exact because we round this off. It's approximately that, 0.42. If I do sine of 154.63, once again, it's also almost identically the same. Not exactly after about the 4th, 5th place, but still the point is they both give you that sine, okay? And both angles are in general possible for a triangle, okay? But what we have to think about then is, are both these possible, okay? So for 154.63, okay, for this angle, then if we add up all the angles, 154.63, plus angle A, which was 40 degrees. That would be 194.63. Okay. And that's basically that's too big to be a triangle. Okay, because remember, all the angles of a triangle have to add up to 180 degrees. And here we're saying just two angles add up 194 degrees. That's too big to be a triangle. Okay, so in this case, B is not going to be the 154.63 degrees. Okay, so we can eliminate that one because that angle would make it something that was not, could not be a triangle. Okay, so what we have found then B is the other angle, the acute angle, 25.37 degrees. Okay. Now, what we've shown then is that for sine of a positive angle could have two possible angles, one in quadrant 1 and one in quadrant 2. And for this, we're able to eliminate one of them because it would give us something that wouldn't be a triangle. Okay, so we found side B. Now, what else do we need to find? Well, the easiest thing now to find is angle C, big C, because now we have two angles. Let's do that. So let's find angle C, where C then is just 180 minus the sum of the other two, so 25.37 degrees, plus 40 degrees, and we can do that in the calculator. I won't go to Desmos to do that on your own calculator. Okay. And the other angle then, C, is going to be 114.63 degrees. So C itself is an obtuse angle, so this is an obtuse triangle. Look back at our picture then we drew, this could have been probably actually a bit wider than that, so C is probably a bigger angle than that, but not too terribly far off. So just remember, when we're drawing a picture from numbers, just remember your picture may not be accurate, okay? But this is kind of close enough to help us out. Okay, let's go back and finish this one off then. Last thing I need to find then is side C, small c. Okay, and so now we can use the law of sines. We know everything else. So I'm going to use this, also use what is also as a general guideline. Try to use what you're given as much as possible. That way, if you made a mistake on something you already calculated, they won't carry through as much. So here I'm going to use, and also the inverted version, use C over the sine of angle C is equal to side A over the sine of angle A. Okay. Once again, plug in the values. If I do that, then I'm going to have C over the sine of angle C. We found that angle C, 114.63, is equal to A, side A, which was 3, over the sine of angle A, and angle A was 40 degrees. And so once again, multiply both sides by this number. So C is equal to the sine of 114 degrees, 0.63 degrees, times this fraction, 3 over the sine of 40. Okay. And then let's just plug that into Desmos and see what we get. So we have the sine of 114.63. And also let's put parentheses around that. So Desmos will know I'm not trying to take the sine of everything else. Then times that fraction. So it's 3 divided by the sine of 40. And my value is approximately, what's going to two places, 4.24. Okay, 4.24. Now, obviously, angle C is the largest angle, so it should have the largest opposite sine, and it does because the other sides were 2 and 3. Okay, so we now solve that triangle. And actually, give me just a moment. I need to make sure I have enough virtual paper here, so I actually need to do a few more sheets. Actually, I have to make sure they have more than enough. Shouldn't take that much, but just to be sure. Okay. All right. So now let's do our next one. So now I want to take a look at one of the ambiguous case where we can actually have two solutions. Okay. let's take a look at this. So this time we have side A is equal to 6, side B is equal to 8, and angle A is equal to 35 degrees. Okay, so somewhat similar to the last one, but actually I'm going to see it's going to be a bit different. So we try and draw a picture of this, and once again, I'll draw kind of a similar one, though this realizing my picture may not actually represent it. Let's say this is angle A here, which is 35 degrees. Okay, let's say this is angle B, angle C. So we said side A is 6, and this is 8. You already see, so the picture's not exactly right. This side's shorter than that, but that's okay. We're just drawing something to help us visualize it. Okay, because we're actually going to see this actually gives us two triangles. One that's an acute triangle with all angles less than 90, and one with an obtuse triangle, one angle bigger than 90. Let's see what happens. So we need to find, and so this is actually the side angle case. The ambiguous case when it's going to be two sides and one of the opposite angles. Okay, so we need to find then angle C, and then also side B, or side B inside. No, wait, no, I'm sorry. Side angles. You define two angles: angle B, angle C, and side C. Okay. So first, and actually in this case, we need to actually have to find angle B first because we don't know anything at all about C. Okay. So if we try to find either angle C or side C first, essentially we have two unknowns in our equation, which we can't, that doesn't work. So let's find B first. Angle B, rather. So big B. And we'll use the law of sines, and we'll use side A, since that's what we know. So we're going to use, apologize, I have a lot of trouble writing things today for some reason, but that's okay. Side B, did it again. The sine of angle B over side B is equal to the sine of angle A over side A. Once again, plug everything in. And so that's going to be the sine of angle B over side B, which was 8, is equal to the sine of angle A. So angle A was 35 degrees over side B, which is 6. Okay, multiply both sides by 8, and we have the sine of angle B is equal to 8 times this fraction, sine of 35 degrees over 6. And once again, let's go to Desmos to approximate that. Once again, about 4 or 5 places. Okay, so 8 times the sine of 35 degrees divided by 6, and that's approximately what's going to do 5 places. So correct it here, it says 76477. So that's the sine of angle B. And so then angle B, if you take the sine and inverse sine of both sides, we have this inverse sine of that value, 0.76477. Okay, let's go back to Desmos and do that. Let's find our angle. And remember also, because inverse sine, the output are basically essentially gives us angles in quadrants 1 and 2, basically, from negative pi over 2 to pi over 2. So that's the reason why we have to consider then what other angles might have in quadrant 2. Sorry, quadrant angle. The output of inverse sine is angles 1 and quadrants 1 and 4, rather. Okay, so we do the inverse sines, which we can go to functions and inverse sine this and just type in 0.76477. Okay, and once again to 2 places, that's approximately 49.89. All right, degrees. Now we know that should be one of them, but once again, we also have to do the same thing. So let's look in quadrants 1 and 2. So of course, you're 0 degrees, 90 degrees, or 80 degrees. So this one angle is one we can use, 49.89 degrees. We also have to find out what angle over here also is, well, the same. So this angle here is also 49. This is your reference angle, 0.89 degrees. Okay. And so to do that, so that angle is going to be 180 minus that. So I'll just do that on my calculator. And that's going to be approximately 130.11. Okay. Now, question then is that too big? All right. So let's look at that larger angle, 130.11 degrees. Okay. If I do 130.11 degrees plus the other angle, which is 35 degrees, okay, that gives us then, you can tell, 165.11 degrees, okay, which is not too big, okay. This is, I'll say this is valid, okay. A valid triangle. Okay, so what we have then, if we kind of draw a picture now, we should have this look something like this. For this triangle, actually, we have two. This side was 8. This side was angle A. And this basically here was 6. So it looks something like this now. This is our angle B, and this is 130.11. Okay. That's side C, and this is small side C. Okay. So that's what this triangle looks like. And then we'll have another triangle, which we use the other angle. Okay. Now, so we need to figure out the rest of this triangle. Okay. So no angle B. Let's find angle C. And of course, that's going to be, C is going to be 180 minus 130.11 plus 35. Okay. And then C is going to be a small angle, about 14.89 degrees. Okay. Good. So then let's find small side C. Okay, that's what's left. And we'll just use C over the sine of angle C is equal to, let's use A since it's already given A. So side A over the sine of angle A, and plug everything in. So C over the sine of angle C, we just found that C, the sine of 14.89 degrees, is equal to A, which was 6 over the sine of angle A, which is 35 degrees. And once again, same as before. So C is going to be the sine of 14.89 times this fraction on the right-hand side, 6 over the sine of 35 degrees. Let's do that on Desmos. Okay. In parentheses, the sine of 14.89 times 6 divided by the sine of 35. Okay. So in that case, we get for C, for this triangle, one version, is 2 places again, 2.69, about 2.69. Okay, so now we found the values then we need to find for this triangle. Okay, I'll just say so. Squeeze this in for one triangle. We have this. Now the other possibility, okay, is the other angle could be 49.89 degrees. Let's draw that. Okay, in that case, we're going to have an acute triangle. And say so This is the second triangle. So this is why we have two solutions. Okay, so our second triangles look like this. So this, once again, this angle here is going to be 35 degrees. Okay, this side is still 8, this side is still 6, but now we have this angle. So this angle here is this is angle B, and this is the one that's what, 40, I forgot what it was, 49.89 degrees. Right. Angle B is 49.89 degrees. So what happens then, as the reason I have two triangles, essentially the situation is, imagine just taking this side right here and swinging it way over here, it makes contact again. That's where we got one triangle, and then swing it back gives us this one. Okay. Now we already know B, so let's find C for this triangle, angle C. And of course, once again, that's going to be 180 minus the sum of the other two. So 35 plus 48.89. Okay, then, and that angle C is going to be actually a little bit larger than 190 degrees. I mean 96.11 degrees. Okay, and once again, that's angle C. Make sure it make a bigger C. All right, and so then finally, then we have to find side C for this second triangle. Okay, use the same relationship we just did. Okay, so C over the sine of angle C is equal to A over the sine of angle A. Plug everything in. And so we have C over the sine of 96.11 degrees is equal to in 6 over the sine of 35. And just what we did before, so we're going to multiply both sides by the sine of 96.11. So the sine of 96.11 times 6 over sine of 35 degrees. And let's plug that into Desmos. In fact, what I'm going to do is I'm just going to copy this and just change the angle in here. And double 96.11. Double check that. Yeah, 96.11. Okay. And that, two places, is 10.40. So for that triangle then is 10.40. Okay, for the second triangle. So that's the result of the ambiguous case. So what happens is, in this case, and we had two possible triangles, where depending on where you connected this side here to the other, give you two triangles. One where this large angle, or one angle which angle B was bigger than 90 degrees, and one in which angle B was smaller than 90 degrees, like we saw here. Okay, let's take a look at one more example. And this time I want to show what can happen if you have no solution. So it's number 4. Okay, so once again, here's what we have. A is equal to 2. C is equal to 1, and angle C is equal to 50 degrees. Now, let's try and draw a picture, although once again, this picture may not be right. Just kind of approach it the way we usually would. So maybe it looks something like this. Okay, so here's side A is 2. Side C, if this is angle A, B, and side C this is 50 degrees. This is side C, and then angle C, and this is side B. Okay, now this, as we said, actually has no solution. So what case is this? Well, this is another side angle case. And then so we need to find angles A, B, and side C. Oh, I'm sorry, side C is 1. Side B, rather. Side C is 1. Yeah, and then side B. Okay. Now, let's try and find A first. In this case, what we know we're given is we know both side C and angle C. We have to know at least one combination of an angle and opposite side to use the law of sines. So let's just use sine of A over side A, which we know. And you actually have to find this in first because we don't know anything about B, either its angle or its opposite side, so we can't start there. Over the sine of angle C over 1. If that's convenient, that just becomes sine of angle C. Okay, once again, plug in everything. And so we have the sine of angle A over 2 is equal to the sine of angle C. And angle C is 50 degrees, so the sine of 50 degrees. Okay, of course, then the sine of A becomes 2 times the sine of 50. Once again, let's do that on Desmos. Okay, because once again, try to do this. It's 5 places, so 5, so it's right here. So put 1.53209. It says 1.55329. But I actually hope you notice a problem because actually we try and do this. Let's try and do this. Okay, once again, going inverse sine functions. 1.53209. You already start to see a problem. It says it's not defined. Okay, what does that mean? Well, basically, the domain of inverse sine is -1 to 1. Okay, it's not undefined since it's divided by 0. It's undefined since it's out of the domain. Okay, but this is not possible. So we can't take, so the domain of inverse sine of x is -1 to 1. Obviously, that's outside of it. Okay, so basically no angle exists to make this possible. Exists to make this possible. Like I said, I'm having a difficult day writing for some reason. Make this possible. So there's no triangle. So no triangle exists. So basically, to try to draw a picture of it, it probably looks something kind of like this. So here's our 50-degree angle. Okay. Here's our side 2, but the problem is opposite side here is only 1. So basically, we can't complete the triangle. So if this kind of goes on forever, we can't make a triangle. Okay, that's what happened. So in this case, this also happened with the the ambiguous case or the size and angle case. You can have, once again, as we saw, a unique triangle, 2 triangles, or no triangle. Those are all possible. Remember, as long as you have as long as you have as long as you have at least 2 angles in one side, you can always have a unique solution, always have a unique triangle. What we've done today then is learn how to solve cases with law of sines, what can happen, and how to find and solve triangles using the law of sines. Thank you. Have a good day.